Welcome to tutorial 9 part 1. Alright, let's go through the questions. First, we look at question 1. Now, two aliphatic compounds A and B which contain carbon, hydrogen and oxygen only are isomers. Okay, they're isomers to each other and they contain C, H and O. That's it. So they can be both oxidized into C and D. So A can oxidize to C, B can oxidize to D. Alright, the table shows the wave number for the main absorptions. Now, as we can see from the tables, A has a wave number of 3,300 absorptions. B has also around the same 3,350. Now let's check the data booklet. 3,300, 3,350. Okay, the absorptions at this range is due to which functional groups? So 3,003 to 3,005. Now these are the two. Okay, so we can see the absorptions are due to is either alcohol or a phenol, okay, due to the OH stretch. So from here we can see A and B both contain OH or a phenol, okay, but here it says the two aliphatic compounds. Aliphatic means without benzene ring, because the compound with benzene ring we call it as aromatic. Okay, so remember, aliphatic means just a normal straight chain or branch chain hydrocarbons with A and B. So this one we can confirm that A and B has an OH group. A and B both alcohol. Okay, with OH group. All right, next, what else we can see from here? Compound C is with two wave number absorptions at 2,000 and 1,030, and D has 1,700. So let's check 1,700 plus from data booklets. So 1,700 plus, it could be due to C aldehydes, the C double bond O stretch, and it could be due to ketones, the C double bond O stretch, as well as it could be due to a carboxylic acid. All right, so these are the possible things that can happen here. And then what about the 2,750? 2,750, I will assume that is this. All right, so this is due to the CH of the CHO stretch of aldehydes. So from here we can see the one with the 2,750, which is compound C here, okay, which is compound C here, is due to an aldehydes. Okay, C is an aldehyde, and D probably due to a ketones or an aldehydes. But in this case, since aldehydes should have a 2,700, for D, it should be just a ketones because it just has the C double bond O without the CH stretching of the aldehydes. All right, so C and D is an aldehyde and ketone respectively. So what we can do from here is we can make a deductions. A and B both alcohol, and both can be oxidized, yes, into aldehyde and ketones, which means A is actually a primary alcohol, B is actually a secondary alcohol, and that's the reason why A oxidized into aldehyde because it's primary alcohol, B oxidized into a ketones. Okay, so now we know A and B. Examine the table above and identify the functional group present. So A and B, your answer here should be just alcohol, OH group. C should be CHO, aldehydes. D should be C double bond O, or you just put ketones. Okay, so that's the answer for part A. All right, let's move on. Part B. Describe a chemical test you could use to provide support for your answer to 2 and 3. Now, if you refer back to 2 and 3, one is aldehyde, one is ketone. So what are the chemical tests you can use for this? I will assume that for B, to test for aldehydes, okay, I will use Tollens reagent. Okay, and what is the observation given is actually giving you a silver mirror if it's an aldehydes. Okay, now for ketones, compound D, for ketones, and how to test for ketones, nothing much, we only have one reagent, which is 2,4-DNPH. It should give you a yellow precipitate. Okay, and of course, to double confirm whether it's a ketones or aldehyde, since 2,4-DMPH actually reacts with both aldehyde and ketones. So once you tested the ketones with 2,4-DMPH, you should test it with Tollens reagent again. And this one should give you no silver mirror. Okay, so that's the reason why we have to confirm that it's a ketones is not an aldehyde when you use 2,4-DMPH. So additional step. Now, of course, you may ask, can I use a Fehling solutions for test the aldehyde? Yes, definitely. Fehling solutions should give you a blue solution changes into a brick red precipitate. That's it. Okay, that's for your B. Now let's look at compound C. Let me erase that. Oh, wait, where is that thing? Never mind, it's okay. So let's say compound C will undergo further oxidations to produce compound E. Estimate the wave numbers of the main infrared absorptions. Now, when C further oxidizes, where is your C? C is supposed to be an aldehyde. So when aldehyde further oxidizes, you should get a carboxylic acid. And what are the absorptions for carboxylic acid? There you go. I have a carboxylic absorption here, which is 1,720 to 1,700. You must have this peak to indicate the C double bond stretch, as well as the carboxylic acid OH, which is, where is the the OH bond for carboxylic acid? Let me see. Am I hydrogen bonded? There you go. 2,500 to 3,500. That's carboxylic acid for the OH group or the COOH. All right. So I should see two absorptions when you oxidize C into further oxidize. So you should have a 1,725 to 1,700 range. This is for C double bond O. And then for OH is about 3,300. Sorry, wait. It should be 2,500. Sorry, 3,500 to 2,500, and that's for your OH. Okay, that's for C double bond O. So these two peaks should appear for your compound E here. Okay, so two absorptions to indicate the presence of carboxylic acid. All right, let's move on. Question 2. An organic liquid X of molecular mass 187.8, so you have the molar mass of that, was found to have a compositions by mass of this percent carbon, hydrogen, and bromine. A sample X refluxed with sodium hydroxide until reaction was complete. After separation purification, Y was found to have the composition of following. So A, calculate the empirical formula of X. Now, if you still remember the calculate empirical formula, let's do it here. I have three elements. I have carbon, and then I have hydrogen, I have bromine. Okay, so how to calculate empirical formula? Let's do this. Take the percentage for each, 12.8%, 2.1%, and 85.1%. And all this is going to divide by its relative atomic mass. So it's 12, 1. Bromine is 79, 79.9. All right, so you divide them, you get the ratio. Okay, and then try to get the smallest ratio, you will get the empirical formula. Okay, so this one is done. I'm not going to show you this because you can do it yourself. And suggest a possible formula for compound X. Now, how are you going to do that? Once you get the empirical formula CHBr, you're going to put a bracket in and put n here equals to 187.8. And from here, you're going to times in, for example, I have two carbon, so it's about 12n plus 79.9n. Okay, if all are 1, it depends on your empirical formula. And then you will get your n value equals to what? Integer, and then you times it in, you will get your molecular formula. Okay, so that's for B. All right, now what type of reaction takes place during the reflux process? Now, very simple here. I'm adding sodium hydroxide excess to reflux it. It's a solution, so which means aqueous sodium hydroxide. And from here, we know it's a halogenous alkene because it's a bromine there. And when you add NaOH aqueous into bromine or halogenous alkenes, all right? So what type of reaction is this? For C, it should be either SN1 or SN2. Either way would do because we can't see the structure. So we know that it must be nucleophilic substitution. All right, so it must be nucleophilic substitution here for C. And last one, name compound Y. So compound Y should be an alcohol. Okay, any alcohol that match with the formula just now from B. Once you got the formula for compound X, you just use this, but changing it into an alcohol because after substitution, your Y should be an alcohol, and just name it. So depends on how many carbon here. If it's 4 carbons and it's butanol, there's 5 carbon pentanol. So just name it respectively according to your molecular formula for this. Okay, so that's question 2. Now, question 3, infrared for A to D is actually representing ethanol, propanol, ethanol, and ethanoic acid, but not in order. So you have to identify A, B, C, D. So give the full structure formula for ethanol, propanol, ethanol, and ethanoic acid. Just showing you here for A. So ethanol, it should be CH3CH2OH. All right, and then propanol should be CH3COCH3. And then ethanol should be CH3CHO, that's aldehydes, and ethanoic acid should be CH3COOH. Okay, so these are the the structural formula. Let's look at B. Examine the spectra carefully and identify the full reasoning, the spectra for ethanoic acid. So ethanoic acid. So what is the structure of ethanoic acid? From the formula, we can see I have C double bond O, I have OH. So I must have these two as options, C double bond O for carboxylic acid and OH for carboxylic acid. So which one do you think is the spectrums for ethanoic acid? So C double bond O, I would say it is always about 1700 to 1600. So this is the one with C double bond O. Check your data booklet again. So this must be the carboxylic acid, and carboxylic acid must have OH. OH always with broad peak here. It's always due to OH. It can be an alcohol, it can be a carboxylic acid. So combinations of OH and C double bond O, we can say D is actually an acid, a carboxylic acid. So your answer for ethanoic acid is supposed to be spectrum D. All right, so let's go for ethanol. Again, what is the functional group in ethanol? I should have OH group. Alkyl group, we just ignore this, CH stretching and bending. So just look at alcohol group. As I mentioned just now, when you have an OH group, regardless of carboxylic acid or alcohol, you should have a broad OH peak. So other than D, which one actually with a broad OH peak? I have it here. See the broad peak? Like a big broad peak here. And this must be due to OH. So there's no C double bond O here. So which means I have an alcohol, and therefore the answer for ethanol is spectrum B. Okay, so that's it for this. Let's look at question 4. Now question 4 is about mass spec. Just now was question 1 and 2 was actually for infrared spectroscopy. So let's look at the mass spec here. These are mass spectrums, relative abundance against mass to charge ratio. For A, suggest a formula for an ion for each peaks in the above spectrum. So what are the ions here for each peaks? First, what are the informations we have? We have C4HO. This is the empirical formula. It is not the actual formula. And these are all the possible fragments. Now, like I always said this, when you're given with this mass spectrum, the first thing you're going to look for the peak with the highest mass to charge ratio, which is this in this case. And this is actually the molar mass. Okay, this is actually molar mass. So I have the molar mass, I have the empirical formula. Let's check this. So CH4O, put N here, equals to molar mass of 32. So carbon is 12, 12N plus 4 hydrogen, 4N plus 16. N, you get 32. And N equals to 32 over 32. So N equals to 1. Therefore, the molecular formula is actually CH4O. That's the molecular formula. Okay, confirm CH4O is the molecular formula, and now we're going to identify each fragments. Now 28, which fragments or what are the atoms that giving you 28? I have 1 carbon, 4 hydrogen, and 1 oxygen, so 28. So let's say I have 1 carbon, which is 12, with an O, which is 16. So this is equals to 28. So this is due to a CO positive. Please make sure you do this because this is the ions that form in a mass spectrometer. All right. 29 means CHO, just additional 1. Or CHO or COH, up to you guys. It's just a fragment. It's just a molecular formula. 30, you get another H, so it's CH2O. Okay, 31, CH3O, and of course, positive. 32, the final one, which is the full, okay, the whole molecule. We call it as the molecular ion peak, so or an M peak. So this is a CH4O. So these are the fragments from the for A. All right, let's look at B. What is measured by the peak height in the birth spectrums? So the peak height is actually measuring the relative abundance, how abundant each fragments here, each identified fragment, CO, CHO, CH2O, CH3O, all this, how abundant are they formed in the machines, in the mass spectrometer? Now this is quite random. So sometimes when you put the same sample in, it might give you a CO is the one that giving you the highest relative abundance because it depends on how they break down the structure, how they fragmented into fragments. So different fragments will have different mass, and different mass, different possibility to form the highest relative abundance. So this is quite random. All right. So that just show you relative abundance. That's it. So let's look at part C. Occasionally, 2 electrons can be removed from each fragments produced. Where will these peaks appear in the mass spectrums if 2 electrons been removed? Now, all these things here appear in a mass to charge ratio. I show all is positive ones because they are actually by default positive 1 charge. Now, what if 2 electrons being removed? When 2 electrons being removed means all this charge will become 2 positive, 2 positive, 2 positive, 2 positive, as well as 2 positive. Now, here is mass to charge ratio. So which means let's look at the peak number 1 here, 28 over positive 1. Therefore, you get your mass to charge ratio of 28. But what if this is positive 2 instead? Then you get your mass to charge ratio of 14. So here the question asks, if 2 electrons being removed, so all of this will divide by 2 because positive 2. So what will be the charge for each of this? Number 1, 28 becomes 14. Let's divide by 2 for all. 29 becomes 14.5, all right, and then 30 half is 15, and then you have 31, so 15.5, that's where they appear on the x-axis, and then 32, then you get 16. So these are the mass to charge ratio for each of these peaks. Just change them into half. Okay, this is where all these peaks appear when the ions are actually 2 positive. Get it? Okay, that's it for question 4. Let's look at the last questions. When an organic compound is passed through a mass spectrometer, some of the molecules are broken down into fragments. The simplified mass spectrums of an organic compound is shown below. Now we have all these ions, 29, 77, 105, and 134. Again, mass to charge ratio here is assumed that is the mass over positive 1 by default unless they stated otherwise. So the molecule is known to be either this on the left or on the right, because these two, they share the same molecular formula. Okay, they share the same molecular formula but different structural formula. So they're both actually having the same mass, which is 134. Remember, this is the one with the highest mass to charge ratio. This is actually the M peak, means the whole molecules. So both having 134 as a molar mass. Okay, and the rest, smaller numbers here are the fragments when they actually broken down into fragments. So let's look at A. Suggest which fragments of the molecule could be responsible for each peak in the mass spectrums. Now, if you look at the structure here, 29. So which part of the molecules actually break down and you get 29? C2H5. This is 29. And by the way, we can't get a fragments of 29 here following this stretch. Of course, you can't break the things like here and then add on with this, these two, you add them up. No, it shouldn't be that way. All right, it should be a continuous chain. So I can see this is a fragment C2H5 that give you 29. All right, what about 77? If you check the molar mass, the benzene ring itself is giving you 77 because it is C6H5 positive. Okay, and that's for 77. And 105 is actually the benzene ring together with the C double bond O, and that's giving you a C6H5CO positive. All right, that's giving you a positive charge. So this is actually the 105. All right, and the 134 will be the whole molecules because that's the molecular peak. All right. Now, by referring to your answer in part A, decide which molecules could have given rise to the spectrums. Explain your choice. Now, to explain this is very straightforward because in these second molecules on the right, there is no fragments giving a peak of 29. Okay, so from this reason, we can see the molecule on the left. Okay, the molecule on the left was the one that given rise to this spectrum. So answer for this is the one on the left due to the absence of peaks 29 or fragments 29 from the molecule on the right. Okay, and of course it's based on how you phrase it. So this is my suggested answer. So you just said, okay, the answer is the molecules on the right and the molecules on the left, sorry, molecule on the left. And why is it not on the right? Because the molecule on the right does not give the peak at 29 because there's no fragments giving a mass charge ratio of 29. All right, so that's it. So this is for tutorial 9 part 1. I will upload tutorial 9 part 2 soon. Okay, let's get tutorial 9 part 1 done. Okay, that's it. Thank you for watching this. I'll upload again. Thank you.